Hi, welcome to this video on solving modulus problems. This is the last little bit of chapter 2, and I kind of wanted to wrap this up today. Because I can't be with you in the classroom, I thought this was the best way to make sure. There's a few parts of this that I just want to draw your attention to, and I thought the best way to do that is to a really quick, or hopefully really quick video. Kind of the next best thing to be in the classroom with you. So again, I try not to ramble too much because I do have a tendency to do that, but just to get through the two examples that we were going to do together in class, and then you can have a go at the final exercise, and then you're ready for the chapter review as well to kind of wrap up this chapter on functions and graphs and things. And then next week we can begin on chapter 3. We're making good time with pure 3. Okay, you are being asked in this example to sketch the graph, state the range, which we haven't really looked at with modulus graphs, I don't think. But obviously we know how to discuss range anyway, and then solve an equation. So it's kind of bringing together different parts of the chapter that you've already done, because we've already solved modulus equations, which is part C, and we've already sketched some graphs, and we know about domain and range. It's just kind of bringing it all together into something that resembles more of an exam question rather than doing all of the different parts in isolation within the textbook. So when you are sketching a modulus graph where there's also graph transformations going on, it's best to start with the most basic modulus graph, which looks like this, where it is, where's the pointer? Where it is, I don't know what you would call it, where like the bottom of the V is at 0, 0. It is symmetrical around the y-axis, with the y-axis as your line of symmetry. That is your basic y equals modulus x graph. From there, we can then start to do the transformations that we have within the function we've got. So we've got a translation in the x-axis, we've got a stretch in the y, and we also have a translation in the y. So I would do that kind of step by step to make sure you get to the final answer. So the first thing they're doing is that -1 inside of the bracket. So that is a translation, so a movement in the x-axis in the positive direction. Remember, we do the opposite when it's inside of the function, when it's happening to x. So instead of doing -1, we are adding 1 and moving everything to the right. So it becomes, I'm going to try and use different colours. So doing the first part, just this -1, I guess it's a turning point. I don't know if you call it a turning point on a modulus graph, but hopefully you know what I mean when I say that. So it now meets the axis at 1. It would still look exactly the same. It would be symmetrical around 1. Mine doesn't really look very symmetrical, but it is just a sketch. We can also, so we know where it hits the x-axis, so we've got like a root there at 1. We do need to work out where it's hitting the y-axis as well, especially because we have this stretch in the y direction as well. So to work that out, to work out where it is hitting the y-axis here, we know every point on the y-axis has an x-coordinate of 0. We can put that into the graph that we've got so far, which is just y equals modulus x minus 1, because we've only done part of the transformation so far. If we put 0 in for x there, we get y equals modulus minus 1, which means y is equal to 1. So it is crossing the y-axis at 1. So again, just to do that a little bit slower, I know that every point on the y-axis has an x value of 0. I've substituted x equals 0 into this, gives me 0 minus 1 is minus 1. taken the modulus of that gives me y is equal to 1, meaning that it crosses the y-axis at 1. Now we can deal with the stretch in the y direction. So we've got its scale factor of 3, we're multiplying it by 3. So now instead of crossing the y-axis at 1, it needs to cross at 3 by multiplying by 3. Maybe it needs to be a thicker line so we can see it. It's still meeting the x-axis at 1, but it is now stretched up in the y direction. So the blue line is y equals 3 modulus x minus 1. So we're almost there. We just have one last step to do, which is to, just change the colour, sorry, which is to do this last minus 2, which is outside of the function, meaning it is a change in the y, in the y coordinate. It's a translation because it's minus 2, and because it's a effect in the y axis, we do it as is. We don't need to change any signs. If it's negative 2, we are translating the graph in the negative y direction, which means that our turning point now, instead of being at 1, 0, is now going to be at 1 minus 2, so down here. And instead of crossing the y-axis at 3, it's going to cross the y-axis at 3 minus 2, which is 1. So it's going to cross here. And it's going to look like, trying to keep it symmetrical, not symmetrical, parallel to that blue line, because in theory it should be, but obviously it is just a sketch. So that green line is our final answer, which I appreciate is difficult to see with all of the other lines on. I wonder if I can rub them off. Not easily. Can I do it like that? No. Okay, never mind. It is what it is. Put the pink one back on. Yeah, so the green line is our final answer. Key kind of points to make sure you've highlighted is that the turning point down here is at 1 minus 2. It's meeting the y-axis at 0, 1. And there's no other coordinates that you need there. You just need those two. Make sure they're very, very clear. Either label them as coordinates like this, or just make sure the correct values on the axes are labeled. Question B is relatively straightforward. Now that we have the graph, again, trying to ignore all the other lines that I have on that graph now. If I just sketch it out quickly, so I have this. This is my final answer. I've got, its turning point is at 1 minus 2. Y-intercept is at 1. The range, remembering range and domain, range is the set of outputs. So output is y. So all of the possible y values that this graph has. So we can see that the minimum y value is negative 2, and then we can continue up and up and up for infinity if we wanted to in the y direction. So our range is f of x, or y, is greater than or equal to negative 2. Really straightforward, very simple, 1 mark. But again, a mark that could be a difference between grades. Then the last part is to solve the equation, which we have looked at already. We've looked at how to solve a modulus, but just really quickly, we remembering that we need to do one with the positive modulus function and one with the negative modulus function. So we're putting them equal to each other. So we have 3 modulus x minus 1 minus 2 is equal to a half x plus 3. Solving it with the positive modulus, we get 3x minus 1 minus 2 equals a half x plus 3. Expand your bracket. And then put all your x's on one side, all your numbers on the other. So we have 2.5 or 5 over 2x is equal to 8. So x is equal to 16 over 5. And then we also need to do it with the negative modulus function. Now, when we do that, the only part where the sign is changing is what is inside of this modulus, the x minus 1. The 3 stays the same sign, this stays a negative 2. It's only the x and the minus 1 where it is negated, where the sign's changed. So that becomes 1 minus x instead of x minus 1. It's still equal to a half x plus 3. And then again, expand the bracket, rearrange and simplify. So we have 3 minus 3x minus 2. X is on one side. I'm going to add my 3x across to avoid it being negative. Gives me 7 over 2x equals, I've got 1 minus 3 minus 2. So x is equal to negative 4 over 7 is equal to x. I'm not going to do it right now, just because, again, I don't want this video to be like 30 minutes long. But please remember to check these values. Okay, so check that x equals 16 over 5 and x equals negative 4 over 7 do actually work in the equation. So if you substitute it back into this, are the left hand and the right hand side of the equations actually equal to each other? Because in some cases they won't be. Again, you can see it by sketching a graph, but personally, my mind works better algebraically. I find it easier to just solve both and then just check that my solutions are valid. So that's the first example done. And that's basically what the questions would be like in the exam, kind of sketching a graph, maybe a mention of range, and then solving some kind of equation involving a modulus. So one last example really quickly before I wrap this up. Given that f of x is 2 minus modulus x plus 1, find the coordinates of the point P, Q, and R. So they've sketched the graph for you. They just want you to work out what the coordinates actually are. And then again, D, solve your modulus function equal to a half x. For part A, some of them are easier to spot than others. So like the two intercepts, for example, for R and Q. So we can work out Q quite easily because we know that every point on the y-axis, again, x is equal to 0, and we can work out what the y-intercept is by just substituting 0 into this equation. So we can do 2 minus modulus x plus 1. That was pointless, where x is equal to 0. Gives us 2 minus 1, which is 1. So it's crossing the y-axis at 0, 1. So Q is 0, 1. For R, we've got the same thing, but this time we're putting the modulus equal to 0 because it's y that is equal to 0, not x if we're crossing the x-axis. Yeah, so we have 0 is equal to 2 minus modulus x plus 1. That is solving a modulus equation. So it's either it's either 0 equals 2 minus x plus 1 or 0 equals 2 minus x minus 1, depending on which part of the modulus works. Solve them both and then choose the one that actually makes sense for the diagram you've got. So if we solve the first one, we have, I'm going to add the bracket across. I have x plus 1 is equal to 2, so x is equal to 1. Seems like it would make sense. X is a positive value because because r is over here. Obviously, it's in the positive part of the x-axis. Or when we do it the other way, we get minus x minus 1 is equal to 2. So minus 3 is equal to x. That one doesn't make sense. So this equation, that part of the modulus equation, doesn't fit our diagram. Well, actually, it's given you the other intercept, isn't it? Which we already know. So we already know that one's equal to negative 3 because they've already labelled it. So we know we're using x equals 1. So the r coordinate is 1, 0. So we've got the two intercepts. The last thing we need to work out is p. We know, because of the structure of the equation, because it's 2 minus something, in this case modulus x plus 1, we know the graph is at its highest. Because we're starting with something and subtracting, we know the graph is at its biggest value when we're doing 2 minus 0. So where modulus x plus 1 is equal to 0. I hope that makes sense. We're trying to minimize whatever we are subtracting from 2 to make our graph, to make our output, the y value, the highest it can possibly be. The biggest it can be is if we're doing 2 minus 0. As soon as the x plus 1 starts to get bigger and bigger, the value of y decreases because we're subtracting something from 2. So it's going to get smaller and smaller. And it can't be negative. We can't get a double negative making a plus because it's modulus. It has to be when subtracting a positive value. I feel like I'm over-explaining this to the point where it could be confusing you further. So we need modulus x plus 1 to be equal to 0, which means that, well, yeah, x plus 1 is equal to 0, so x has to be negative 1. So when so this means our x value here is negative 1. We then need to work out the corresponding y value by substituting minus 1 into the function. So if x is minus 1, y is 2 minus, we know it's 2 because we made it 0, didn't we? 2 minus 1 plus 1, which is 2 minus 0, which is 2. So for p, the coordinate is minus 1, 2. Again, I feel like I've really overcomplicated working out p when it's pretty straightforward. We need to make the modulus part of the function 0 in order to get the highest possible value, the highest possible output for y, and we need to, and by doing that, we get our highest positive, sorry, I'm tripping over my words because it's getting towards my bedtime, it's nearly 8 o'clock. We are making the modulus part equal to 0 so that we can maximize the output, the y value, at its maximum. Y is 2, and that occurs when x is equal to negative 1. So where the maximum point of our graph is negative 1, 2. Again, I feel like I've really talked around something that's really quite simple. So I do apologize if I've just confused you. The last part is to solve f of x is equal to a half x. I wasn't anticipating to go on to an extra slide. So it's 2 minus modulus x plus 1 is equal to a half x. Now again, solve it using both the positive and the negative part of the modulus. So we're going to do it 2 minus x plus 1 is equal to a half x. And then we're going to do 2 minus x minus 1 is equal to a half x. Okay, expand the bracket out, go all your x's on one side. It's a linear equation. It's straightforward enough to solve. So we have 2 minus x minus 1 is equal to a half x. I'm going to add the x across. So I have 1 is equal to 3 over 2x. So x is equal to 2/3. And then 2 plus x plus 1 is equal to a half x. I'm going to subtract the half x, so I get a half x is equal to negative 3. So x is equal to negative 6. Again, I'm not going to do it. I'm not going to do it right now, but please remember to check that these values are actually valid for the equation you've got. Substitute them back into your equation and double check that the left-hand side actually is equal to the right-hand side, because occasionally, not always, but we have to watch out for it anyway, occasionally your solutions aren't actually valid because your graph might only intersect once instead of twice. This one does intersect twice. These are both valid solutions. So we do get x equals 2/3 and x equals negative 6. But please remember, really, really important, especially in exam, to double check that your solutions for a modulus equation are actually valid and they actually work. Right, that's it. I'm going to stop talking. You have exercise 2G to have a go at to practice this, and then have a go at the chapter review before the lessons next week so we can wrap up this chapter on modulus, functions, graphs and that kind of stuff and move on to, I'm pretty sure it's trig next, but I could be wrong. I'll need to double check. Of course, if you have any questions, please come and find me. Ask me on Thursday. I know we have stats, but please ask me if there's anything about this lesson that you're unsure of. Please ask me on Thursday. Or come and see me in my CCA on Wednesday lunchtime. Right, guys, have a great day, and I'll see you on Thursday. Thanks for listening if you've listened this far.